Hi, my name's Delandre, and I'll be walking you through one of the most interesting celestial bodies known as the black hole. I'll be describing their formation, creation, structure, as well as their effects on space and time. A key concept of understanding the creation of black holes is the Schwarzschild radius. Let's start by defining what the Schwarzschild radius is. According to Einstein's theory of relativity, it's possible for anything to become a black hole as long as they are compressed down to a certain point. This point is called the Schwarzschild radius. The Schwarzschild radius is a sphere. Whenever a given object's mass is compressed within this sphere, the gravity becomes so strong that its escape velocity, the amount of energy required to escape, becomes equal to that of the speed of light. This is the point at which an object becomes a black hole. What's amazing is the fact that you can find the Schwarzschild radius yourself anytime you want, simply by knowing the mass of an object. This equation might look complex at first, but it's actually really simple when you understand what all these letters mean. The two letters on the left side of the equation, Rs, collectively represent the value of the Schwarzschild radius, and the letter M represents the given object's mass. The capital letter G represents the gravitational constant, while the lowercase letter c represents the speed of light. The gravitational constant will always have a value of 6.67 times 10 to the negative 11th power, and the speed of light will always have a value of 3 times 10 to the 8th. When you substitute or plug these values into the equation, you can find the value of the Schwarzschild radius for any mass you desire. Once we know the Schwarzschild radius, we can then find the volume and density of the area within the Schwarzschild radius. Once again, it's relatively simple once you know what the letters mean. In the top equation, the two letters Vs collectively represent the volume of the Schwarzschild radius, while the symbol being multiplied by 4 is pi, which some of you may recall as being 3.14. Again, Rs is equal to the Schwarzschild radius, with the lowercase m in the bottom equation representing the given object's mass. The Greek letter rho on the left side of the bottom equation represents the density, so really it's just the basic equation of density equals mass divided by volume. So when will an object ever be crushed so small? Well, most black holes are formed from the death of massive stars. When a star is no longer able to support itself through the fusion of elements in its core, which it often stops doing at iron, nothing will be stopping the star from collapsing on itself except electron degeneracy pressure, the temporary point at which the electrons in a star's atoms can no longer be squeezed any closer together. Eventually, the electron degeneracy pressure gives out, entering into a state of electron capture, in which they collapse into the nucleus, turning protons into neutrons. When the core of a star becomes nothing but a dense ball of neutrons, the star's supernovas. In stars over 20 times larger than our Sun, even the neutron degeneracy pressure gives in, compressing the mass of the star remnants past its Schwarzschild radius, forming a black hole. Now that we know how black holes are created, let's move on to some of their characteristics. Black holes possess three physical properties: mass, charge, and angular momentum. A black hole's mass can be any positive number, but a black hole's charge and spin are restricted by its mass, and we'll take a look at this relation in the next slide. This inequality demonstrates the relationship between a black hole's mass, charge, and angular momentum, where Q is the charge of the black hole, J is its spin, and M is its mass. The value on the left will always be less than or equal to the black hole's mass squared. Black holes that have both sides of this inequality equal to each other are known as extremal black holes, which are purely theoretical at the moment. Some black holes have no rotation or spin. These black holes are called Schwarzschild black holes. Let's take a look at another characteristic of black holes known as Hawking radiation, theorized by Stephen Hawking. Hawking radiation is, in theory, the small amounts of radiation given off over time by black holes, causing them to lose mass over time. However, because these emissions of Hawking radiation are so small, only smaller black holes will shrink over time. Most black holes can maintain and actually gain mass faster than they lose it simply by absorbing the cosmic background radiation. Now let's take a look at the effects black holes have on things around them. Light particles passing by a black hole become bent inwards toward the black hole, which distorts the appearance of objects. This effect is known as gravitational lensing. The other two gravitational effects, redshift and time dilation, are both observed from the outside of a black hole. If you were sitting at home watching an object fall into a black hole for whatever reason, you would see the object gradually falling slower into the black hole, taking an infinite amount of time to actually fall in. At the same time, the object would be growing dimmer and redder until eventually becoming invisible due to the effect of the black hole's gravity on the wavelength of light. Now we'll be moving on to the parts of the black hole, starting with the event horizon. The event horizon is the point of no return. Once past the event horizon, nothing, not even light, can escape, and we can see the effects a black hole's gravity would have on light to the right. Far away from a black hole, light particles can move freely, unaffected by the black hole's gravity, but as they move closer to the event horizon, their paths become bent inwards. This is where you get the gravitational lensing effect. Once past the event horizon, all particles will be headed toward the center of the black hole, known as the singularity. Singularities are simply the points of infinite density located at the center of black holes. They can be either ring-shaped and rotating black holes due to their spin stretching the singularity out, or they can be a single point in static, non-rotating black holes. The photon sphere. The photon sphere is a region of zero thickness located about 1.5 times away from the black hole's Schwarzschild radius, or event horizon. If a light particle touches the photon sphere moving at precisely the right angle, the particle becomes trapped in an orbit around the black hole. However, this orbit is extremely unstable, and the smallest change, such as pieces of matter entering the black hole, will alter the path of light in the photon sphere, causing particles to either gravitate inward toward the black hole or move away and get flung back into space. To the right, you can see the likely paths light would take as it approaches a black hole's photon sphere. The ergosphere is characteristic of rotational black holes. It's an oblate sphere located outside a black hole's event horizon, in which it is impossible for anything to stay still due to a process called frame dragging. Anything that comes near a black hole will immediately begin moving in the direction of the black hole's spin. If an object simply wanted to stay still, it'd have to move faster than the speed of light. However, it's possible for objects to escape the ergosphere using the black hole's rotational energy, which could eventually stop the black hole from spinning at all. The accretion disk is that bright spiral of matter you see being pulled inward by the black hole in the picture to the right. Accretion disks are formed not only by black holes, but several other compact and heavy objects, such as neutron stars, which are held up only by their neutron degeneracy pressure. Gravity and friction squeeze and compress the matter falling in, making it extremely hot. When this happens, electromagnetic radiation is given off. In objects as heavy as black holes and neutron stars, the frequency of electromagnetic radiation given off can be as high as X-rays. Now that we know how black holes are formed, what they do, and the parts of a black hole, let's take a look at some interesting types of black holes. We'll start simple with collapsar or stellar black holes. The stellar black hole is essentially what we've been learning about throughout this video. They are simply small, relatively speaking of course, extremely dense black holes formed from the collapse of stars. Supermassive black holes, on the other hand, are pretty impressive and can be billions of times larger than our Sun, and have a Schwarzschild radius of up to 400 astronomical units. Just to put that into perspective, 1 astronomical unit is equal to 150 million kilometers, or 93,000 miles. They are believed to have been formed by stellar black holes absorbing other stars and even merging with other black holes. Most scientists agree that there is a supermassive black hole located in the center of most galaxies, including our own at Sagittarius A. Another fascinating type of black holes are quantum mechanical or micro black holes. They only have a mass the size of our moon and a radius of around 0.1 millimeters. Due to their size, they are expected to lose mass from Hawking radiation faster than they can gain it. And if micro black holes exist, we may be able to detect some of them exploding at the end of their lives pretty soon. What's more interesting, though, is the fact that it may be possible to create them through high-speed collisions, such as those that occur between particles within the Hadron Collider. The last type of black holes I'll be describing are called primordial black holes, and primordial is just a sciencey word for the beginning of time. That's what primordial black holes are. Black holes formed after the first few moments of the Big Bang, in which temperatures and pressures were so high that black holes could form from just about anything. Primordial black holes could be as big or as small as any other black hole, meaning they could be classified as micro or supermassive, depending on which one you're looking at. Another thing about primordial black holes that makes them so interesting is that the tiny primordial black holes that exist could be particles of dark matter. And that's it. I hope you enjoyed listening to all this sciencey stuff, and I definitely hope you learned something from it.